Welcome to Module 4. Calculus is often divided into two interconnected parts, differential calculus and integral calculus. In this module, we lay the groundwork for differential calculus, which largely concerns rates of change. A rate of change is a measure of how a quantity changes with respect to another. Some instances include the rate at which data moves through a network, the rate at which computing resources, like CPU and memory, are utilized, the rate at which cost, revenue, or profit changes with respect to market conditions, the rate at which a population, such as people, money, computer viruses, cybersecurity threats, or many others, change with time. There are lots of other examples. There is an old Aesop tale about a race between a tortoise and a hare. The tortoise trails along at a slow but constant rate from start to finish. The hare, on the other hand, starts out running fast, but halfway through realizes that the tortoise is so far behind that she has time for a nap. After she wakes up, she resumes her fast pace towards the finish line, but is just beaten by the tortoise. Let's think about the average speed of the tortoise and the hare. Speed here is a rate of change. It's the rate at which the distance is changing with respect to time. The tortoise has a slow but steady pace, meaning that his average speed is consistent. The hare, much quicker on her feet, starts with a high rate of change, but then stops for a nap. Even when she resumes her rapid pace, the time spent sleeping lowers her overall average speed. As a consequence, the tortoise ends up with a greater average speed over the race duration, securing his win. Suppose, though, that instead of talking about the average speed, we are interested in the speed at a particular moment. For the tortoise, this rate doesn't change. It's the same at every point in the race. But for the hare, it varies greatly, from very fast when she's running to zero when she's napping. Think about looking at a speedometer in a car to see the exact speed at a single point in time. This is different than the average speed over an entire trip. Now, let's apply a word to this concept of instantaneous rate of change: derivative. For now, think of the derivative as a snapshot of the rate at which one thing is changing with respect to another at any given moment. For the tortoise, the derivative of his position with respect to time is constant. The derivative of the hare, however, is not constant. It changes depending on when we look at her. When she's sprinting, her derivative would be a high value, indicating a rapid change in position over time. During her nap, however, the derivative would be zero, since her position is not changing at all in that moment. We'll bridge the gap between the average rate of change and instantaneous rate of change, that is, the derivative, with an example. The data usage of a network over time is defined by f of x equals x squared plus 2x, where f of x is the amount of data used in gigabytes and x is the time in hours. To find the average rate of change from x equals 2 to x equals 5, we calculate the slope, y2 minus y1 divided by x2 minus x1. Well, this is f of 5 minus f of 2 divided by 5 minus 2, which is 35 minus 8 over 3, or 27 over 3, which equals 9. The average rate of change between the second and fifth hour is 9 gigabytes per hour. Now this represents the slope of what's called the secant line, a line that connects 2 points on the function's graph. Now, let's consider the rate of data usage at exactly hour x equals 3. Here, we will use what's called the tangent line, a line which touches the graph only at x equals 3. Finding the slope of this line is trickier, since it's based on a single point instead of two like the secant line. So how do we handle finding the slope of a tangent line? The key lies with limits. Consider a general point, x, f of x, on the graph of f of x equals x squared plus 2x. Now let's identify another point that is h units away from this x value. The new point has coordinates x plus h, f of x plus h. Notice how the secant line approaches the tangent line when we make h smaller and smaller. It stands to reason then that the slope of the secant line would approach the slope of the tangent line as h approaches 0. Now, the slope of the secant line is y2 minus y1 over x2 minus x1, which equals f of x plus h minus f of x over x plus h minus x, which simplifies to f of x plus h minus f of x over h. So the slope of the tangent line is the limit as h goes to 0 of f of x plus h minus f of x over h. So let's find this limit for the function in our example. So the data usage is given by f of x equals x squared plus 2x. And we want to find the slope of the tangent line here. So we do this by finding the limit as h goes to 0. We have f of x plus h minus f of x. All that goes over h. Now for this function, that would be the limit as h goes to 0, and f of x plus h would just be putting x plus h in place of x up here in this function. So we would get x plus h squared plus 2 times x plus h. All right, and now we're going to subtract f of x, which is this function. And remember, we have to subtract this entire function. So I'm going to put this in brackets. And that would just be x squared plus 2x. And all of that goes over h. All right. Well, I think we can see here that if we stick h in here directly, we would end up with a 0 in the numerator and a 0 in the denominator. So we can't evaluate this just by substituting 0 in. So what we do is some algebra. So we have here the limit as h goes to 0. Looks like we can do a good amount of simplification up here. If we multiply x plus h quantity squared out, that would give us x squared plus 2xh plus h squared. And put this 2 inside these parentheses would give me 2x plus 2h. And we're going to subtract off this part, and so that negative applies to everything in these brackets, which would give me a negative x squared minus 2x. And all of that goes over h. Well, I think we can see here that we have an x squared and a 2x that would cancel with this negative x squared and this negative 2x. So this gives us the limit as h goes to 0. And let's see, the x squareds are gone, so we're left with 2xh plus h squared. The 2x's are gone, and we are left with this plus 2h right here. And I'm going to factor out an h in the numerator. So it looks like that leaves me with 2x plus h plus 2 with an h outside right there. And now that h can cancel with this h. It looks like that will leave me with the limit as h goes to 0. And I would just have 2x plus h plus 2. And if I now substitute the 0 in place of h, then this term right here just goes away. The whole thing just equals 2x plus 2. So the slope of the tangent line for any given value x is given by 2x plus 2. Now we were interested in the rate of data usage at exactly our x equals 3, so we can find this instantaneous rate of data usage to be 2 times 3 plus 2, which gives us 5 gigabytes per hour. There is a lot to unpack here. Note that when we calculate limit as h goes to 0 of f of x plus h minus f of x over h, we get a new function. This function, denoted by f prime of x, is called the derivative. So, to summarize, The derivative of f of x is defined as f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. And it represents the slope of the tangent line at any given point. Furthermore, this slope tells us the instantaneous rate at which the y values are changing with respect to the x values. Let's look at some examples. A cybersecurity team models the volume of network traffic anomalies with the function n of t equals 1/3 t to the fourth minus 15 over 2 times t cubed plus 12t squared plus 6,600. This is where t is greater than 0 and where t is the time in hours since the start of the workday at 8 o'clock a.m. The derivative of n of t is n prime of t, which equals 4/3 times t cubed minus 45 over 2 times t squared plus 24 times t. In part A, we wish to find how many anomalies are there at 1 o'clock p.m. Well, to do this, we first note that 1 o'clock p.m. is 5 hours past 8 o'clock a.m., so we know that t is equal to 5. So we just need to find n of 5. Now n of 5 is equal to 1/3 times 5 to the fourth minus 15 over 2 times 5 cubed plus 12 times 5 squared plus 6,600. Now we can just throw this in the calculator. What we find is that this is equal to 6,170.83. So there's approximately 6,170.83. Maybe we round that to 6,171 anomalies at 1 o'clock p.m. In part B, we want to find the rate of change of network anomalies at 1 o'clock p.m. Now the rate of change of network anomalies at 1 o'clock is the value of the derivative at t equals 5. So we find n prime of 5. And we know that n prime is equal to 4/3 times t cubed, so that would be times 5 cubed, minus 45 over 2 times 5 squared, plus 24 times 5. Now when we plug this in, what we find is that we get negative 275.83. So, in other words, at 1 o'clock p.m., the number of anomalies is decreasing by approximately 276 per hour. For part C, we want to know, are the number of network anomalies increasing or decreasing at 6 o'clock a.m.? Well, first of all, note that 6 o'clock a.m. is 23 hours after 8 o'clock a.m., so t equals 23. And so to find whether it's increasing or decreasing, we're going to take a look at the derivative at t equals 23. So we get 4/3 times 23 raised to the third minus 45 over 2 times 23 squared plus 24 times 23. And so when we plug this in, what we find is that the derivative is about 4,872.17. The number of network anomalies is increasing, and by quite a lot. You can see from the example that the derivative gives us valuable insights. But using the limit definition to find the derivative can be quite complex. For now, let's put aside the process of finding derivatives. Don't worry, we'll get to this in time. At the moment, it's useful to focus on interpreting the derivative. A file compression algorithm is modeled by C of S equals 100 over 1 plus 0.001 s, where s is greater than 100. Here, s is the original file size in megabytes, and C of S represents the percentage of the original file size after compression. The derivative is C prime of s, which equals negative 0.1 over the quantity 1 plus 0.001 s squared. In part A, if a file has size s equals 500 megabytes, what percentage of this size will the compressed file be? Well, we know that C of S represents the percentage of the original file size after compression. So if a file has size S equals 500, we have C of 500, which equals 100 over the quantity 1 plus 0.001 times 500. This gives us about 66.67. The compressed file will be about 66.67% of the original size. Does the percentage of the compressed file size ever increase? Well, we can use what we know about compression to answer this. Compressed files are always smaller, so the answer is no. However, when we look at the graph of C of S, this also becomes apparent. File sizes are on the horizontal axis, and as they get larger, the value of C of S gets smaller. Another approach here is to look at the derivative. The derivative has negative 0.1 in the numerator and a squared term in the denominator. Now, squared terms are always positive, which means that the overall fraction will always be negative. So the derivative, which represents the rate of change, is always negative, meaning that the file size never increases. Lastly, we can also see from the graph that the slope of the tangent line is always negative for any points along the graph, which tells us the same thing. The file size never increases. Part B. Suppose that we define the efficiency of the compression algorithm at a particular file size as E of S equals the absolute value of C prime of S. Which file sizes yield higher efficiency with this compression algorithm? Larger or smaller ones? Okay, so we are defining the efficiency as the absolute value of the derivative. So let's take a look at the derivative of a smaller file size, say something like S equals 300 megabytes. The derivative is C prime of 300, which is approximately negative 0.05917. So the efficiency would be positive 0.05917. Now let's take a look at a larger file size, say S equals 1,500 megabytes, which is 1.5 gigabytes. Note that the efficiency here has dropped to 0.016. Looking at various values for both small and large file sizes shows that the efficiency is smaller for larger file sizes. Let f of t equal 10t squared minus 50t plus 300, and this is the number of website visitors per hour, where t is the time in hours since a marketing campaign was launched. The derivative is f prime of t, which equals 20t minus 50. A. What does f prime of 0.5 mean? F prime of 0.5 is the rate at which the number of website visitors is changing per hour. Now we find that f prime of 0.5 is negative 40. So half an hour since the marketing campaign was launched, the number of visitors is decreasing at a rate of 40 per hour. Now there are various possible reasons for this decrease. It could be due to the initial curiosity waning or technical issues with the website. Part B. After how long does the rate of change of visitors switch from decreasing to increasing? So we want to know how long it takes for the rate of change of visitors to switch from decreasing to increasing. I'm going to reword this. The question is, how long does it take for the derivative to change from being negative, which means a decrease, to positive, which means an increase? So the real question is, when is 20t minus 50 negative and when is it positive? How about we start by finding the value of t for which the derivative is 0? We have 20t minus 50 equals 0, or 20t equals 50, or t equals 50 over 20, which gives us 2.5. At our t equals 2.5, the derivative is 0. Now it's fairly straightforward to see that the derivative is negative when t is less than 2.5, and it is positive when t is greater than 2.5. So the rate of visitors changes from decreasing to increasing at t equals 2.5 hours. In this module, we talked about what a derivative is and one way to calculate it. We looked at how a derivative shows the instantaneous rate of change at any given moment. Calculating derivatives directly from the definition can be tricky, Luckily, we'll learn some easier ways to do this in the next module.